real pleasure to introduce Dr. Tenio Popmintchev, who's going to give the talk, his talk today. Tenio was an undergrad at the University of Sofia before coming to JILA to do his PhD work. And for his PhD work, Tenio solved theoretically how to generate the first essentially tabletop X-ray laser. And then within a couple of years after graduating was able to demonstrate experimentally that the ideas actually work. And of course this work was done with the Becker group here at JILA and with collaborators in Vienna and in Cornell. And what you're going to hear about today is that actually, so Tenio was very delighted to show that his PhD work was correct and generated a new type of light source. But since then, he's actually discovered a few more ways that you can actually make bright tabletop X-ray beams. And so I'll hand over to Tenio to tell you about his work.
Thanks a lot for the introduction, Margaret. Good afternoon, everyone, and thank you for taking your time to attend my talk. It's my pleasure to show you some of our work that we have developing, that we have been doing in the last 4 or 5 years. In fact, on a couple of continents. So for the first time, we can generate bright coherent X-ray beams with a record for a tabletop 7.7 angstroms wavelengths. So we use for this the process of high harmonic generation. What is also equally important is now we think that we can generate X-rays with arbitrary spectral, temporal, and polarization shapes. So when the laser was first invented, scientists were looking at it as a solution, looking for a problem. So as we know it from more than half a century, the laser transformed science, technology, also society and economy. So the laser development was actually undergoing a small revolution. Besides the first UV laser, there were lasers developed near-infrared, visible, and ultraviolet. And what is actually quite discouraging is actually the first excimer laser that was giving us a wavelength of about 190 nanometers is still the only widespread laser short wavelength. In fact, this wavelength is just less than 4 times shorter than the first UV laser. Certainly, there are few other approaches that can use short wavelength lasers, but they are not in widespread use. And this is where our research can make an impact and provide solutions for short wavelengths with many surprising properties that I will show you. So why it was so challenging to build an X-ray laser? So people, of course, realize the large impact that it may have. However, they also realize that it's quite hard to do. So to convince ourselves, we can look at the Einstein coefficients for spontaneous and stimulated emission, and we can see that if we want to create a laser, X-ray laser based on population inversion, the power scaling is quite unfavorable with the laser wavelength. So this, what this means in absolute values is that, for example, I can use a couple of triple A batteries and power a laser pointer at about 1 micron and double it. Actually, this is what my laser pointer is. However, the power requirements for a 1 nanometer laser wavelength or 1 angstrom are quite substantial. So people realized back at the time that nuclear weapons have similar power. They are on the similar scale. And now if you look at the declassified project back in the mid-80s, if you search online, you can see that people were doing experiments where they're detonating pretty much atomic bombs to generate X-rays in the same region of the spectrum where now we can do in the lab without So this same power scaling is the reason why the first true X-ray laser actually came with about 50 years of delay. And indeed, this large-scale X-ray three-electron laser is based on different physics, acceleration-based physics. And well, which is prohibitive if we want to make a small-scale laser that we fit in our labs. To do so, we use a different approach. We use nonlinear optics, and it took just 1 year for Franklin actually to generate the first second harmonic beam, 1 year after the invention of the laser. So the first fluid laser already had the electric field strength to drive the electron in a nonlinear motion and to generate harmonics of this beam of multiples of the fundamental. So the way to think about this regime is we simply were combining a couple of photons of the fundamental and creating a single photon with twice the photon energy. Well, this beam was so weak that even when this paper was published, the editor deleted the point here on the photographic plate, thinking that this is actually a piece of dust. However, it took another year for longer than to give us a recipe how we can make this beam extremely bright and usable for applications. You can see that the pace of development was pretty much one year rate for a new discovery. So this recipe will be used also in our high harmonic generation process, which is an extreme version of second harmonic generation that I showed you. In this process, in principle, we can combine hundreds of photons together to create a single one in the X-ray regime. Well, this process, the high harmonic generation is a universal response of atomic molecular systems when they are illuminated by femtosecond process. It's well understood within a simple model where in the strong field, the atom is ionized and the electron is accelerated in the external field. Well, since we have oscillating driving field, the electron can be returned back towards the parent ion, and the excessive kinetic energy can be emitted in the form of high energy photon. Well, this regime is actually quite interesting, also because it seems to be quite favorable. We can easily access the X-ray regime by increasing the laser intensity or by increasing the laser wavelength. Well, this is kind of quite naive way of thinking, and I'll explain why this is not so trivial. Well, we like to think about high harmonic generation as the coherent version of the Brownian X-ray tube. Well, we are familiar that in the Brownian X-ray tube, we first blow electrons and we use a high voltage power supply to accelerate the electrons towards the material target. Here we have collision ionizations, which leads to Brownstrown emission, and which is incoherent in 4 pi. What we have done in our experiments, we have replaced the high voltage power supply with a coherent laser field, which allows us now to achieve full control over the emission. Well, how does the same picture looks quantum mechanically, and how we do the coherent control in high harmonic generation? What you see here is a movie. This was done by our collaborators. This movie was done by our collaborators Luis Plaja and Carlos Fernandez Garcia. You can see that what it shows is that every half cycle of the laser, we have a fraction of the electron wave back in the beam, ionized, accelerated, and returned back, superimposed with the rest of the electron wave function that is at ground state. This creates very strong oscillations, and this is actually our emitting dipole. What is quite remarkable about high harmonic generation is that it can emit light from the infrared up to the X-ray region simultaneously. So this is, if you think about it as a laser-like source, in fact, it's much more than a laser. So, well, we can go beyond the quasi-one-dimensional picture where we can pretty much shape the electron wave function along the polarization of the laser. We can also achieve two-dimensional control, having fully coherent driving field. For example, in this case, presented over here, we can use circuit polarized driver, and you can see that we can create an electron wave function like with a beautiful spiral shape. And in fact, this is the most useless case of control because the electron wave function does not return back. This simply means that there is no recombination and no emission of any photons. Well, we can expand the two-dimensional control. For example, we can add a second laser field, Now, with this said, we counter-propagating polarization in this case, and we can, for this particular example, we can return the electron several times and actually modify the properties of the generated X-rays. Well, with this said, I would like with this slide to pretty much summarize, to outline what we're talking about, and summarize most of our current capabilities. For the first time, we know how we can generate harmonics from the infrared, the vacuum, ultraviolet, extreme ultraviolet, up to the Q electron volt X-ray region of the spectrum. Also, for the first time, we can generate a broad X-ray supercontinuum, very similar to the supercontinuum that you get from a Röntgen X-ray tube. What is quite remarkable that this spectrum spans more than 12 octaves. In another extreme, now we know how we can manipulate the laser wavelength in a way that we can generate highly monochromatic light. We can generate a single harmonic with a bandwidth which is almost 1,000 times narrower. Furthermore, as I already kind of briefly mentioned, that we can change the polarization of the driving field, and we can actually now generate both linearly or circularly polarized high harmonics. As probably you have heard from Dan's talk yesterday, these harmonic beams have full spatial coherence, and we are able to make we are able to make these beautiful images with near wavelength resolution. We have full control also in the temporal domain. We can generate femtosecond to attosecond pulses. We can control the pulse duration. We can either get an isolated X-ray burst or a train of pulses. Well, as you see, we have if in the past we were happy to generate any X-ray photons, now in fact we can achieve almost full control of the generated X-rays, and we can do this optics free at the moment of the generation. And this is extremely important because X-ray optics are either of very low efficiency or not available in many regions of the spectrum. So, as you have seen from Dan's talks yesterday, we can make really beautiful images. However, if we want to capture the fastest processes in nature, like let's say something faster than the nanosecond and picosecond time scales which are accessible to electronics, now we need to use ultra-fast light. For example, the first steps in vision or in photosynthesis, they happen on the scale of picosecond to hundreds of femtosecond. And the fastest dynamics outside of the nucleus, like any electron-electron correlation, are on an attosecond time scale. For example, it takes for an electron in a hydrogen atom about 150 attoseconds to orbit. So there are even faster processes, faster interactions inside the nucleus, which just from its uncertainty principle are suggested to be on the z-second time scales. Well, with this said, we can convince ourselves that if we want to access the fastest dynamics outside of the nucleus, we need to have Q electron volt X-rays. In other words, the ultra-fast attosecond X-rays are the ultimate strobe light to capture the fastest motion in our natural world. So in this talk, I will be focusing about, I will be talking about three surprising regimes of high harmonic generation, and all three of them can extend the emission into the X-ray region of the spectrum. First of them originated from my PhD work. It involves, it uses infrared lasers and gently ionized atoms. As I already mentioned, with this approach, we were able to generate X-ray supercontinuous spanning, extending up to 1.6 kilo electron volt. In the second approach, we have been able to generate X-rays with contrasting properties both in the spectral and temporal domain. In fact, instead of we were using X-ray wavelengths in the opposite region of the spectrum instead of in the UV region. And furthermore, instead of using atoms, we started using ions. For the first time, we found their proper place where they can be useful. They have been known in the past that they can extend the emission. For the first time, we can do this in an efficient way. So, as you already see, the spectral structure looks like a frequency comb in the X-ray regime. We can go even further. So, this is a regime where we can mix a couple of laser frequencies, and we can also manipulate their polarization to generate X-rays with very unique spectrum. The spectrum, well, the example that we'll be talking about, but this regime is much more general than this, is generating harmonics with circularly polarized polarization, actually with counter-rotating felicities. Well, as I already mentioned, the pace of discoveries in perturbative nonlinear optics was pretty much 1 year, and here it took us about 25 years to figure out how we can phase match this process. And why this has been so challenging? Well, you can think about it that in a typical interaction region, we have more than 1 trillion actually atoms, so more than the population of the Earth. And what we need to do now, we need to synchronize the emission both in space and time using our quantum conductor, our infrared laser. So if you think about the spatial and temporal scales, things are quite amazing. Now we are talking about driving laser wavelengths in the visible to mid-infrared range of the spectrum, and X-ray wavelengths 1,000 times shorter wavelengths. The amount of control that we achieve requires that we need to add in phase the fields with sub-angstrom resolution and actually sub-attosecond temporal resolution. This is kind of quite amazing. Imagine that if we had to do this using electronics, we'll be limited pretty much to the nanosecond or picosecond temporal scales. Now if we can phase match the process here, probably actually our laser and nature does this passively for us. So since we deal with fully coherent light to get the bright emission from many atoms, we must phase match the process. So in extreme nonlinear optics, we can talk also about phase matching, also as well as about group velocity matching, and I leave the second topic for the last minutes of my talk. What is important difference from perturbative nonlinear optics is that most of the harmonics that we generate now are in the extreme ultraviolet on the X-ray region of the spectrum, and they travel with the speed of light in vacuum. So the only thing that we need to take care of is the propagation of the laser. So if we force it to propagate also with C, then the process is phase matched. So what means phase matching when we have traveling waves with different frequencies? It simply means that we need to lock the peaks of these fields of the carrier with respect to each other as we go to the next atom. And this will ensure an in-phase emission and quadratic growth of the harmonics with a number of atoms. So of course, this is not the case in high harmonic generation. So this process is much more violent. In a sense, we destroy the medium. This process is accompanied by strong ionization of the atoms that we use. What ionization does is actually splits the phase velocity of the laser with respect to the harmonics, and you can easily expect here phase accumulated as we propagate and destructive addition. So this is still oversimplified picture of high harmonic generation. Well, this process is also known instantaneous. So now we have a laser cycle on the femtosecond time scale, in some cases even attosecond time scale. We have an excursion time of the electron also on the femtosecond to attosecond time scales. We have also emitted wave on the same time scales. Now, pretty much the phase of the driving field and its amplitude, the phase of the electron that it accumulates along its trajectory, as well as the phase of the laser recombination, all the matter, and they are imprinted in the newly generated light. So with such a complication and so many dynamics, like the ideal scenario would be to repeat the same picture of the next atom, and this is not trivial. Why? Because we don't propagate through vacuum, and the laser field evolves. Well, we can easily change the amplitude and the frequency of the laser. However, if we have at least half a cycle with the same amplitude and phase, the electron will scatter in an absolutely identical way, and this will lead to constructive addition of the generated light. So this may look quite kind of a strong restrictive regime with a lot of dynamics hard to achieve in the lab, but in fact it's quite straightforward. So, in principle, we can use the neutral atom dispersion. This is pretty much the gas pressure in our interaction medium. We can adjust it to predominantly shape the front of the poles. So this is since the atoms are not ionized, they will be pretty much at the front end of the poles. They will be pretty much reducing the phase velocity here to below c. Now we can adjust the laser intensity, and since ionization kicks in a little bit later during the pulse, the laser, the strong ionization will be creating plasma, which will be speeding up the phase velocity. Thus, for just a limited temporal window, we can balance these two dispersion, and we can achieve phase matching. Well, as you see here, like if we talk about second harmonic generation, we pretty much were able to phase match the processes. You know, if we just simply adjust the angle of the polarization of the driver with respect to the crystal axis, and we can use the biafringence of the crystal to achieve phase matching. Here, all the phase matching actually is a time domain problem. This is the reason why it took us a while to understand how to manipulate the efficient upconversion. What is quite interesting to figure out, to point out, is that in the last several years we figured out that this temporal window is actually a function of the laser color that we use. So, what is also quite remarkable is with such a physical understanding, with almost no numerics, we can use a simple textbook equation about the dispersion of this cycle and capture most of the macroscopic physics, both quantitatively and qualitatively in some cases. So, how does phase matching looks as a function of the laser wavelength? What you see here is a generalized picture of phase matching for high harmonic generation, where we have shown that if we increase the laser wavelength towards a medium array, actually the maximum photon energy that we can achieve with useful flux for applications also increase. Counterintuitively, we have to use longer laser wavelength to get shorter and shorter X-ray wavelengths with maximum efficiency. Well, this may look as very simple extrapolation of physics towards the decay region of the spectrum. However, the initial understanding was that high harmonic generation, phase matching is not possible beyond the UV region of the spectrum, mostly because people were generating harmonics using titanium sapphire lasers. This was the reason also why attosecond science was limited just in the UV region of the spectrum to about 150 electron volt. We have validated all these regimes using different laser wavelengths, and it pretty much took us 1 year from a data point to another data point, simply because the laser technology was not available, or worldwide we were looking for a source. We found one in Vienna, and it took us a while to work together with Andrews actually to build a 4-micron laser with the right parameters for high harmonic generation and extend the emission to above 1.62 electron volts. It's quite interesting to point out also that the UV lasers actually don't allow to extend the matching above the UV region of the spectrum. And well, this is not our current understanding. In fact, I'll explain later why. Well, this is not the full picture. If you are doing second harmonic generation, you may think that if you have phase matched the process, you have the brightest emission. In fact, in high harmonic generation, you need to worry about the emission from a single atom. Well, it was well known that if you increase the laser wavelength due to quantum diffusion, and the electron wave packet will be spreading more and more as we increase the laser wavelength, and well, proportionally as we increase the laser pulse duration. Well, there was a teaching away going towards a medium laser wavelengths, and it looked like the dumbest idea. Simply because the punishment that the penalty that you need to pay here is emission per atom that scales very unfavorably with the laser wavelength to the power of -5. Well, in fact, it turned out that there is a beautiful convergence of macroscopic and microscopic parameters such that phase matching for infrared lasers actually required, well, tens of atmospheres. And we have been working closely with the machine shop here in JILA to build high pressure waveguides that can withstand more than hundreds of atmospheres. These are pretty much kind of were expected pressures for very long infrared laser wavelengths. In fact, we validated this regime using almost every available laser wavelength from the UV up to 4 microns in the mid-infrared with the parameters, with the femtosecond pulse durations and energies that are optimal for harmonic generation. In all the cases, we generated UV to X-ray beams which were undistinguishable from laser beams. All of them, when we were doing Young velocity diffraction, were showing very high fringe visibility. Well, this is a summary of experimental data where I show spectra from the same gas, where we have increased the wavelength initially from the titanium sapphire wavelength in the near-infrared towards 1.3, 2 microns, 4 microns. As you can see, we were able to generate broader and broader X-ray supercontinua centered at shorter and shorter X-ray wavelengths. Well, in fact, this X-ray supercontinuum is still, well, it still holds the record for the broadest supercontinuum spectrum generated from any source, large or small scale. And if you just assume flat phase and do Fourier transform, you can see that it can in principle support the pulse as short as 2.5 attoseconds. This regime is also scalable. Longer wavelength can give you even broader bandwidth, and potentially we can provide the frequencies required to reach also Z-to-second time scales. Much further than this, actually nature wants to make, to force this emission to happen also in a single X-ray burst, and I'll explain why later. Furthermore, if you look at this pulse duration, it actually corresponds to a single cycle at the central wavelength of the spectrum. Well, it's well known that the harmonics are not generated self-compressed. In fact, these are calculations performed by Carlos and Andreas Becker's group, where we can see that the pulses are strongly chirped to about 3 orders of magnitude longer pulse duration. What is encouraging here is that actually the spectral phase is regular, and potentially we'll be able to compress it if we find a way to do this. So, to further validate our understanding of phase matching, particularly in the time domain, we had to figure out how the temporal window scales. And to do so, we performed an experiment where we adopted a technique from the visible region of the spectrum called Fourier transform spectroscopy. So the need for this was because the generated supercontinuum, we are not sure that they are true supercontinuum. Well, it may be a problem of the resolution of the instrument, or also what we also needed to figure out is how the number of burst scales, or in other words, how the width of the temporal window scales with the laser wavelength. So what we did is we simply split the generated X-ray beam into 2 replicas of each other, and we interfered them on the surface of an X-ray CCD. So what this allows us is directly, as we just obtained delay between the 2 pulses, allows us directly to count the number of X-ray bursts. Furthermore, in a way, this interferometry is a super resolution spectrometer. It in fact has a resolution in the spectral domain much significantly greater than the separation of a couple of harmonics, which will allow us to say this is a true supercontinuum. And simply from Fourier transform, if you have a supercontinuum spectrum, you can expect to have a single burst in the time domain. Well, again, we work closely, Chris and Mincheng work close with the machine shop, the guys in the JILA machine shop, to achieve a temporal resolution of about 1.5 attoseconds or 5 angstroms, which were required for this experiment. So this is some experimental data from this series, where in blue you can see the X-ray burst from a driver of titanium sapphire wavelength, or longer 1.3 and 2 microns, as expected for a non-phase match geometry where we have very low pressure, very low peak intensity. We can have a large number of X-ray bursts. As we start increasing the intensity and the pressure and reaching phase matching conditions, you can see that first the number of cycles strongly the number of X-ray bursts strongly decrease for the phase match conditions up to a point where for a 2-micron driver, in fact, we isolate a single X-ray burst. So in the past, this was only possible if you drive the process with a single cycle driver. Now we have no choice, but for any pulse duration, we always will be generating an isolated pulse in the medium region of the spectrum. So this is the first unexpected regime. The second one, which involves UV lasers and ions, actually was discovered when Dimitar and I were trying to validate this UV region of the spectrum, and we were in fact increasing the laser intensity and seeing brighter and brighter harmonics and shorter wavelengths. Well, this was kind of the unexpected part here was that in fact we always thought that ions are something that we need to avoid. Why? Because what phase matching in the infrared teaches us is that we can operate at very low ionizations only, and we can achieve full phase matching only of about a fraction of a percent if we go deeper in the infrared region of the spectrum. Why is that? Well, if you look at the index of refraction, which we need to force it to be equal to 1, we need to balance the atomic and the plasma dispersion. Since the atomic dispersion is very low in the mid-infrared spectrum, we can tolerate very low plasma dispersions. And this is illustrated now here in this cartoon with the phase velocities. The atomic dispersion slows down the phase velocity of the laser, and the plasma dispersion speeds it up. And we can achieve full balance in this picture. Things are quite interesting in the UV regime, and I'll kind of analyze them in two perspectives, macroscopic and microscopic. We have a couple of those. So I'll start by analyzing the index of refraction of the atoms. If we start from the infrared toward and we move towards the UV region of the spectrum, the index of refraction of atoms actually start to increase. Why is that? Simply because we approach resonances of atoms. So ions have exhibit similar behavior of their indexes, and what is quite well, and also what is much more important is now the index of refraction of ions is comparable to that of atoms. Why? For example, imagine a large ion, like large atom like xenon, and with large number of electrons. If you remove one electron, the dispersion slightly decreases, but it's almost the same. So a large neutral atom dispersion simply means that we can balance very high plasma dispersion, which will boost phase matching. Also, in addition, plasma dispersion is less experienced less by these UV drivers. In other words, this is also beneficial for phase matching. So we have also boost from the emission from a single atom. As I mentioned, as we decrease the laser wavelength, now we can expect reduced quantum diffusion. For a laser wavelength 3 times lower than the one of the titanium sapphire, we can expect a boost per atom greater than probably 3,000-4,000 under phase matching conditions. Well, if we assemble this regime, we can see at first glance everything shrinks in the time domain. So in other words, we may even expect that the generated X-rays may be of short pulse durations. Well, furthermore, well, as I already mentioned, the electron wave function can shrink in the spatial domain, which gives you a boost per atom. So in this regime, we cannot achieve index of refraction very close to 1. But what is quite interesting is now we can balance very large plasma dispersion. Why? Because in addition to atomic dispersion, we have ionic dispersion of the same side. And furthermore, we may have several ions at the same time trying to counteract the plasma dispersion. This is shown here in this cartoon where, for example, we can have argon 3, 4, 5 plus here counteracting a very strong plasma dispersion. Well, this is some experimental data showing discrete harmonics again in the X-ray region of the spectrum. So pretty much this is maybe our most pure X-ray frequency column that we have generated in this region. And what is quite interesting is actually that the emission from neutral argon terminates at about 30 electron volts, and all the rest of the emission up to the water window of about 290 electron volts originates from different argon species up to argon 5+. Well, with so much species, it's quite interesting to look at the time domain and look how the phase matching window scales from a different perspective now. We already know that shorter laser wavelength means broader phase matching window, but there is additional kind of physical aspect that I want to emphasize here. So what you see here is a plot of the ratio of the plasma of the phase mismatch due to the plasma dispersion, and the phase divided by the phase match due to the atomic and ionic dispersion. What this simply allows you to gauge is how much the atomic and ionic dispersion can counteract very strong plasma. If you see a vertical curve as the blue one over here, with very large angle, it will simply mean that actually you can counterbalance very strong plasma dispersion. And this is the case if we consider only atoms. If we add the indices of diffraction of ions, we can see that this curve bends up to a point where over a large temporal window we can achieve very small change in the phase mismatch. So contrary, if we use the Tenio sapphire laser, we can see that the dispersion of atoms and ions in, is not enough actually to broaden the temporal window. So broader temporal window, again from Fourier transform, means that we can generate narrower line width harmonics. And this is our record today. We have lambda over delta lambda of about more than 4,000, and as we have heard yesterday from Dan Staub, this is in favor of phase matching. You can achieve better quality images, and this will also help the speed of the reconstruction algorithms. So furthermore, since the harmonics are well separated, they are now separated by twice the photon energy, and we use high photon energy, short wavelength driver. Now the harmonics are separated about 10 electron volts, and in this particular region of the spectrum, we can use bandpass filters, metal filters, which we use anyway to suppress the fundamental light and isolate a single harmonic. So this is not the only example. We can isolate harmonics in many regions of the spectrum. So it's quite interesting to look also at the pose durations of the generated X-rays. They're also contrasting the regime of mini-infrared given harmonics. So if we use UV laser, you can see that we can generate 105 attosecond X-ray burst. So this is very close to the transform limit for this particular bandwidth that we use. If we do the same bandwidth selections for harmonic driven by titanium sapphire, we generate 3 times longer X-ray pulse. Well, why is that? First, you can think about of your laser cycle as your compressor. For example, for a UV driver, we're talking about already of a driver with a cycle which is actually in the attosecond time scale. There is no chance for the electron to be rescattered and be generated with a pulse duration longer than a half a cycle of the driver. Furthermore, well, these are typical diagrams in high harmonic generation, so-called time frequency diagrams, from which we can read a lot of information about the generated light. So the slope of this intense light that you see over here indicates the amount of chirp that we have. So what was quite unexpected in this regime is that, well, it was well known that the aperture scales as the cycle duration of the driver divided by the maximum energy that we can generate. And it was quite intuitive to figure out that if we use UV lasers, we can compress the attosecond pulses. What was not intuitive is that we can generate very high photon energies. And this is where the boost in phase matching and single atom yield helped us. So the last regime that I'll be talking about involves frequency mixing of two colors with counter-rotating polarizations. And in fact, this was a work done quite recently in our group, pretty much a few weeks ago, and was just accepted for a real pulse deadline. In fact, almost all these three surprising regimes were there. It's a nice coincidence that they were all presented as real pulse deadline papers. So how do we generate circularly polarized harmonics? Well, it's, as I already kind of mentioned, using circularly polarized driver does not allow you to generate circularly polarized harmonics simply because you turn off the emission. Instead, if you add a second field with a counter-rotating polarization, now you can generate a combined field with such a complex shape. You have probably generated similar cloverleaf decision figures when you have played with oscilloscopes with a couple of channels. What this allows you in high harmonic generation is to manipulate the electron wave function, and it allows it also for the electron wave function to come back pretty much 3 times in this particular example to the parent ion and give you particular properties of the generated harmonics. For example, in addition to the conservation of energy that we typically have in high harmonic generation, in this example where we use titanium sapphire and second harmonic, we have additional conservation of spin angular momentum. Pretty much we need to keep in mind that the newly generated photon needs to carry away a spin of 1. So this leads to combined selection rules where every third harmonic is actually forbidden, and each pair of harmonics have counter-rotating polarizations. This is shown here in this experimental spectrum. We have a series of counter-rotating polarizations and a missing harmonic. Well, the only thing that I have not shown here is actually the momentum conservation or phase matching, which is required to get bright beams. Typically, if we have linearly polarized light, actually the phase matching here is limited by the fact that we have different dispersion in the two frequencies. It's quite easy, in fact, as we propagate the medium, the combined field to be strongly reshaped, up to a point when driving fields are different enough to destroy phase matching. Well, things are much more simpler when we have counter-rotating frequency mixing, simply because any phase slip in group or phase velocity actually is transferred as a rotation of this into a rotation of this cloverleaf, which is not of a great significance when we talk about generating circularly polarized harmonics. This way we have much more simpler and robust phase matching regime. Well, it took us about 25 years to figure out how we can extend phase matching from the UV region to the XV region of the spectrum. Now that we have built the alpha-beta phase matching in the UV and mid-infrared region of the spectrum, it took us just a couple of weeks or so to figure out that we need longer wavelength drivers to extend the emission into the X-ray region with circular polarized characteristics. So we have also used this slide to study some of the properties about the gadolinium iron multilayer magnetic material. This material was identified in the past as a potential candidate for data storage, since you can switch the spin, you can switch the magnetization direction optically using data line. So what you see here is actually this worm-like structure where we have magnetic, when we have oriented spin orientation perpendicular to the plane, or in opposite direction also perpendicular to the plane. So when we have circularly polarized light, actually left-handedness and right-handedness exhibit, they have different absorptions with penetrate this material, and you can observe, in fact, this in a so-called X-ray magnetic circular black reason, where you need to operate near an absorption edge. This is the gadolinium absorption edge at 145 eV in the soft X-ray region spectrum, and we can now flip the orientation of an external magnetic field parallel or perpendicular to the sample and record two different spectra. The differential signal shows change of sign for left circular polarized versus right circular polarized harmonics as expected, confirming that we have alternating handedness of the harmonics, plus also indicating that we have very high degree of circular polarization. Well, what are the limits of high harmonic generation? What we know at the moment is actually that we don't know what are the limits. In fact, we can keep extrapolating the X-ray wavelength to about 50 microns. And in fact, if we build a laser at about 20 microns, we should be able to reach the 20 kV region of the spectrum. And this would correspond to a conversion process of an order greater than pretty much 500,000, if I remember correctly. However, this is just the phase matching picture. There we have identified some physical mechanisms that may limit our flux, and I will try to address the challenges in high harmonic generation in the X-ray region, like pointing out 5 frontiers. In the other regime, so the greater known is pretty much the indices of refraction of the media, and this is our bottleneck. We have started working in a large collaboration with several groups in different institutions to turn our theory into a predictive theory. Well, in the past we were making small steps. Now we will be doing the same steps in combination with theory and going toward the hard X-ray region of the spectrum. The first challenge that I want to illustrate, this is the brightness of the harmonics. Well, I'm not talking about the maximum photon energy that we can reach, but the maximum photon energy that we can reach with useful flux under phase matching conditions. So we have extended the bright emission up to a few electron volt. Can we scale the physics by another order of magnitude or not, up to 10 electron volt? Well, these were simple calculations that we were doing back at the time, since still supercomputers were not as powerful. You can use simple analytics and predict the flux shown here in vertical dimension as we go towards hard X-rays. What you see here in the bottom of this complicated plot is simply the phase matching limits for medium-wave lasers, and as I mentioned already, vertical scale is our brightness. So what is quite remarkable about this regime is that we may expect even increase in the X-ray flux going to about 10 electron volt. It's completely unknown what to expect for UV-driven high harmonic generation, and the questions that we'll be answering here is what are the phase matching limits and what will be the flux. Same questions we'll be answering for the regime of frequency and polarization mixing. And I'm talking about here not only about counter-rotating driving fields, but fields with linear polarization, cross-polarization, plus co-propagating or counter-propagating beams. This is really a rich regime where we can achieve very strong control on many levels. So the second frontier that I want to illustrate, this is the time domain structure of our policy. So what you see here on the horizontal scale is the laser wavelength. On the vertical scale is the pulse duration of an individual pulse. Now, by changing the color of the laser, we can control the duration of an individual X-ray, starting from about 10 femtosecond down to the attosecond time scale. You can see that what the bottom curves in this plot show, in fact, is the shortest pulse that we can achieve if we are able to compress this emission. In fact, for a 10 micron driver, we may even expect to reach attosecond time scales. On contrary, if you use UV lasers, the emission is almost near transform limited, and it will be quite easy to achieve compression. Well, of course, to be honest, compression in this regime would require very strong attenuation, which will make the flux pretty much not useful, and we need to be looking for new compression techniques. One such an example could be using frequency mixing, where pretty much the idea is to create a laser cycle, effective laser cycle, which have a UV duration. This will automatically give you shorter pulses. So another frontier is, I will illustrate with a little bit more kind of details from the teaching of high harmonic generation. What you see here is again the laser wavelength, and this is the critical ionization, the ionization above which we cannot phase match the process. What is quite remarkable is that for 2 orders of magnitude of laser wavelengths, we need to have a span of ionization of about 4 orders of magnitude. So, well, in fact, it would be quite hard to achieve this in if we have different physics, but tunneling ionization. In fact, what we know about tunneling ionization is that it's independent of the laser wavelength and it's exponentially and scales exponentially of the laser intensity. In other words, with a tiny change of the laser intensity, you can cover this whole range of ionizations. So, as indicated by this curve, is also that for 10 micron laser, we need to use very low ionization and a very low laser intensity. You may think that actually the magnetic field is insignificant. However, this is not the case. Now we have electrons which have quite high kinetic energy, plus our laser cycles are quite long. There's enough excursion time for the electron to be affected by the Lorentz force. What may happen at some point as we increase the laser wavelength is that the electron wave packet may drift away from the parent ion and may never return. And the drift here is along the k vector of the laser. So the spread of the wave packet may not be enough to overlap with the electron in the ground state, and this will greatly reduce our flux. Well, the same question needs to be answered for UV drivers. Well, it's even more interesting there. If we have ion of stronger Coulomb potential, is this ion going to refocus the electron wave packet or not? So it's even kind of more interesting when we mix frequencies and polarizations. This behavior here is, can we return in this scheme the electron wave packet or not? So I will use the same background pictures to explain different physics now. Well, it will be related to the quantum diffusion. So the pictures that you see here are pretty much experimental data of the electron momentum in x and y direction. And y direction in this particular case coincides with the polarization of the laser. So you don't need to know much about the details of all these pictures. What I want to focus your attention to is that when we have tunneling ionization, the electron momentum actually very strongly correlated with the polarization of the laser. When we have multifocal ionization, actually they exhibit more isotropic distribution. So what is quite interesting is that when we phase match the process, actually for all these laser wavelengths that I pointed out, it's quite surprising that actually the electron distribution is correlated with the polarization of the laser, and which indicates that phase match harmonic generation favors tunneling ionization. The question that we have not answered yet is, do we have higher yield per atom from tunneling ionization or multifocal ionization? Well, another interesting question is what happens when we have multiple charge ions, in which of the regimes we are. So, well, and of course, again, the third regime is unexplored. You may think, even also when you mix a couple of frequencies, you may again achieve an effective field of UV polarization, where the scattering of the electron will be restricted to very short time durations, which simply means that you'll be reducing quantum diffusion. So pretty much the way I see it is this will be probably one of the ways to compress the electron wave packet. So I will finish with another challenge. This is related to group velocity matching. For the mid-infrared range for the mid-infrared phase matching range that I mentioned, in fact, we are operating at very high pressures on the scale of 40 atmospheres. What this leads to is a lack of the envelope of the driver at the exit of the medium with respect to the envelope of the driver at the input. This lag can pretty much reduce the electric field in some cycles and destroy phase matching. Well, can we combine phase matching, group velocity, time window in all these three regimes? What would be the amount of flux reduction if we experience such group velocity walk-off? What would be how the phase matching time window will look in ions with respect to group velocity matching? And of course, again, the third regime is widely explored. What will be So the significance of group velocity matching was already indicated in some of the calculations of Carlos for regime that we explored experimentally. In particular, if you try to use a laser of few driving cycles, you can see that due to group velocity walk-off, you can completely kill the phase matching window here, shown in yellow. While, if you have a multi-cycle driver, any lag the envelope is actually insignificant, well, has insignificant influence simply because you have almost flat top envelope. This pretty much does not close the phase matching window, and we can reach very high pressures, very high propagation distance required to achieve efficient macroscopic conversion. Well, effectively what we are after is we are in search of the ultimate driving regime. We are in search of phase matching combined with effective group velocity matching, which I refer to as a quantum-pair phase matching. What this means is simply we would like the electron to have the same quantum pair phase on every atom as we propagate through the medium. So with this slide, I would like to point out that hypermonic generation are already addressing major challenges in materials. Well, we have been working in the last 10 years mainly in the regime. So some of the experiments have led to major discoveries. We have studied nanoscale heat transport in nanomaterials. We have achieved control of material state, control of magnetic state, via spin currents. As Dan pointed out also yesterday, we can make very high resolution images with almost near wavelength resolution. So it would be nice if we can scale all this experiment in the X-ray region of the spectrum, simply because of the penetrating power of X-rays, we can explore much thicker materials. We can also take advantage of the element selectivity. In the X-ray region, we have plenty of absorption edges. So this last slide shows the power of our technique. In fact, there are many imaging approaches which have very high spatial resolutions like SEM, AFM. There are many really visible infrared imaging techniques. We have also nanoplasmonic probes. However, the major advantage of hypermonic generation is combining the high spatial resolution due to the very short wavelength of the emission with the very high temporal resolution of this source, which can reach currently pretty much from picosecond to microsecond temporal scales. Well, so before I finish, I want to thank to all the funders, students, collaborators. I have worked closely with Min-Cheng, who is now on a tenure track at Taiwan. So we have performed some experiments with him in Vienna, the group of Andrews, Boltushka. Pretty much we had a campaign on the scale of 2 years over there. I have worked with Tenio Popmintchev on the regime of UV-driven harmonics, here also with Chris Mancuso and Franklin Dower. With Tintin, we extended the emission from the UV into the X-ray region of the spectrum for circular polarized harmonics. We work also with the magnetic team in our group. So we have very strong collaboration with the group of Andreas and Miško Bekar here in Boulder. We have pretty much 4-year collaboration with Carlos, even before he was here. He is now on the Maria Curie grant. We have been working with his advisor, Luis and Salamanca. So there are another nonlinear effects that I did not mention in hypermonic generation, and we are addressing the challenges there with the group of Alex Beretta at Cornell. And in this is a refraction of the medium, we are figuring this challenge with Temple University and Livermore, with the groups led by Robert Levis and Stephen Levy. Well, this work has attracted also the attention of some federal funding agencies like DARPA or multi-university research infrastructures, and our work was referred as one of the main motivations in this grant calls. Thank you very much for your attention.
Tenio. Any questions?
You had at the very end some slides or some pictures of some of the things that could be done with these out-of-cycle pulses in the time domain. Could you just elaborate on a couple of interesting applications of time resolved, experiments that could be done with the out-of-cycle pulses?
So currently most of the experiments are we are focusing on material science. So are you talking about some of the applications in the X-ray regime? Yes, you may think that pretty much for natural systems you may calculate most of the parameters. Nowadays there's enough theoretical understanding in some experiments. However, if you try to build a nanostructure and study function, the only way to do so is to have this super resolution microscope, which is heteromogenization both in the time and in the spatial domain. So, for example, one experiment that we can be pursuing is actually, I can give an example with circular polarized harmonics. Where we have this gadolinium iron sample, and in fact, what is interesting here is that you can use the magnetization direction as your binary function where you can store it as 1 and 0. Right? You can switch the direction optically, and what is quite interesting is to study, for example, with the temporal harmonics, the limiting factor, how fast, the limiting physics, how fast we can switch the domains. Well, these domains may not be the most interesting structures. So people have, for example, proposed to do the reading of the data by applying electrical currents. However, these domains can merge, and this is not the best structure there. Another topological structure in this case that can be self-preserved and it's much more pixelated that we can study in perspective of building actual devices. So this is
so you can see like a spin wave from your class.
They're called skyrmions, and they are pretty much very small with maybe. Yeah, okay.
In one of the slides, actually you show by the two pulse interference, you can see the pulse trend of the harmonics. That's Fourier analysis of harmonic pulse trend. So I just wonder if this carrier frequency is that real measurement of the carrier field is the real measurement from experiment or?
So I guess you're referring probably about the time domain studies where we have split the X-ray beam in two and we have performed Fourier transform.
Exactly.
So, and you were asking about
the carrier
wave.
Yes.
Yeah, this is extracted from the experiment. Let me go back. So.
Yeah.
Yes, all this data under the envelope here is extracted from the experiment, so we have pretty much 1.5 attosecond resolution. There are a few data points very significant. In fact, what this experiment is missing, it simply actually is a measurement of the Fourier transform of your pulse. So such an interference tells you that, for example, 70 attosecond of a kind of fluid mass over here corresponds, in fact, to a 35 attosecond pulse duration. So as in the actual pulse duration